Okay, so I think we will want to start proceedings for the keynote speech. So welcome everyone who's logged in. Good morning, good afternoon, good evening, depending on what part of the world you're in. I'd like to introduce you to Dr. Tianzhen Hong, who is giving the keynote speech. He's a senior scientist leading the Urban Systems Group at Lawrence Berkeley Laboratory in California. And his research employs interdisciplinary approaches to explore technologies and human factors, supporting the planning, design, and operation of energy efficient, demand flexible, and climate resilient buildings at different scales. His interests cover a large range of topics in the built environment and a highly cited researcher. And perhaps he's best known for his research on the influence of occupant behavior on energy use and adaptive responses. And he's led International Energy Agency energy and buildings and community projects in this area. He's also an IBIPSA Fellow and an ASHRAE Fellow. The title of the talk, hopefully you can see that, is Nexus of Building Decarbonization, Sufficiency, Energy Efficiency, Demand Flexibility, and Climate Resiliency. So the talk should last about 30 minutes, and there'll be an opportunity for questions following the talk. So you can either post questions in the chat section on the website, or at the end we can raise your hand and we can take questions at that point. Okay, so I'll hand over then to Tianzhen Hong to give his keynote speech. Thank you.
Good morning, good afternoon, good evening. I'm Tianzhen Hong, a senior scientist with Lawrence Berkeley National Laboratory. I'm honored and very happy to share my thinking and research about building decarbonization as part of the IBIPSA International Building Simulation Conference in Shanghai. I see 4 essential dimensions to building decarbonization, including sufficiency, energy efficiency, demand flexibility, and climate resiliency. If we look at the evolution of cities, we will see urbanization and economic development play a significant role. So the image just shows an example. This is the financial district of Pudong, Shanghai. The image on the left shows that's how the district looked like in 1987, just a few years after China started economic reform. Image in the middle and on the right, it shows after 25, 35 years of development and urbanization. There's many new buildings, high-rise buildings, mega tall buildings were built. And these, of course, create lots of jobs, creates lots of GDPs. At the same time, it also requires a lot of energy and water services. And it creates, heat that get down to the urban environment. If we look at the building level, right, the human history, right, we started with the igloo that basically consumes no artificial energy. The only source is the solar from the sun. The Egypt pyramids about the same. And then we have modern facilities and structures. The water cube, this Olympic facility in Beijing, except buildings in London, and the super mega tall buildings in Middle East. In the middle, we have these modern design buildings that use a green roof and large open spaces to encourage natural ventilation and use of daylight to reduce the use of electricity. So how we get to those kind of buildings, right? Design operated on top of the changes we are seeing today. So the global climate change, right, that give us challenge of global warming, at the same time, more frequent, more intense, and more widespread extreme weather events, right? So on top of that, we are seeing changes in the energy supply. For example, the electric grid now is changing because of during the middle of the day, We have lots of energy produced by solar. So this is the famous dark curve. It shows the net loads on the power grid in the state of California, right? And when the sun is set, you see there's a huge ramp of energy demand increase, right, till the evening hours. At the building site, we also see the demand is changing, right? Now we have this concept called green interactive efficient buildings that may have EV charging, that may have rooftop PV, may have energy storage, and a lot of sensing and smart controls. So buildings are changing from pure energy consumer, taking electricity from the power grid, to now it can modulate its energy consumption. Sometimes it can also provide energy back to the grid, if able and needed. So globally, the CO2 emission is about 36, billion tons. And you can see this dip in 2020. That's about 5% reduction because of a global COVID-19 pandemic. But in 2022, then we see a 1% increase from the 2021. So this trend is growing. And if we take a close look at the end users, the buildings industry basically emits about 38% of the global CO2 emission. And that includes the operation as well as the construction of buildings. So to decarbonize buildings, we see this is the 4 key dimensions is the nexus for building decarbonization. First is the sufficiency. And this is about reducing the need to use energy down to the satisfaction of useful and well-set energy target. Second dimension, this is energy efficiency. It's about reducing the amount of energy needed to satisfy a given level of energy service. The third dimension is the energy flexibility, and that's about managing energy demand based on weather conditions, occupant needs, and grid signals. And the fourth dimension is about the climate resiliency. So how can we reduce climate change related risk of buildings by adapting building design operation? So globally, the ACEEE, ECEEE, and the India's counterparts together developed these 12 strategies to set up global efficiency. And as you see the list, this includes efficiency for buildings, transportation, and industry. And you look at the top, this is about net zero energy, water, right, carbon buildings and homes. How can we better design these kind of new buildings, right? Increase the stringent codes adoption and enforcement. How can we retrofit our buildings and homes to be more efficient? How can we develop and adopt low energy cooling technologies as the developing countries are facing needs of cooling? And how we use smart buildings and controls, how we electrify our end users in buildings, how we tighten up the efficiency requirement of appliances and equipment, in addition to the industry and transportation and the power grid technologies. So ASHRAE Standard 90.1 basically describes the minimal requirements for commercial buildings that can be built in the United States. And it started in 1975. That's just right after the first global oil embargo. And then every 3 years, it went through a cycle and tightens or increased the energy efficiency requirement. So the target to 2030 is to reduce 80% of the energy used by buildings compared with the 1975 baseline. And then the remaining 20%, it may be met by on-site clean energy generation. And that's the way to get to zero net energy buildings. So we have scientists at LBNL, Jerry Benjamin, did a study for the US national building stock. Basically, the result shows the US building stock can reduce CO2 emission by up to 91% compared with the 2005 levels, right? With the aggressive deployment of efficiency and electrification, as well as a fully decarbonized grid. And this is the US target to get to 100% clean economy by 2050. So APRIA also provides a technology roadmap. These are like a portfolio of technologies, including electrification, efficiency, flexibility, and clean energy generation to help us meet carbon neutral buildings. And if you look at electrification, a lot is about using heat pump for space heating, cooling, water heating, and use of electricity, cooking, and laundry, right, as well as provide smart panels to facilitate charging loads and PV generation. If we look at some technologies, and we can look at how they evolve and what the futures can be. One example is the windows. It started as a single pane clear glass in 1970s, right? So that's a U value about 1. This in IP unit. SI unit is about 5.678. And they then progress to double pane windows, to low E coating, which meet Energy Star requirements. And now we are talking about in the future that will be highly insulated R10 windows, which also provides the dynamic capability to regulate the solar heat gain, depends on the space heating and cooling modes. Lighting is another example, right? Incandescent light started in 1920s with an efficacy of 14 lumen per watt and up to 1,000 hours of lifetime. We then go to fluorescent, efficiency up to 97 lumen per watt, and then go to LED lighting, which is popular today, have an efficacy of 132 lumen per watt, and with a lifetime up to 50,000 hours. Still, if we look at theoretical limit, the natural light has a limit, at 555 nanometer that produce lights at 683 lumens per watt. So we still have a long way in terms of technology limit. For the HVAC systems, we see there's a potential between the good design and high efficient equipment. This is a figure table shows the efficiency design of a traditional chiller plant for large buildings. So conventional design, we're talking about system efficiency 1.75 kilowatt per ton. State-of-the-art design basically reduce it to 1/3, to 0.609 kW per ton. And if you look at these components, basically chiller efficiency improved by 30%. So a lot of improvement is about a pump, how we deliver air, how we move water around, and use available speed controls. So those improvements are on all of the magnitude, up to 10, times improvement. If we look at the water and air heating system efficiency, we definitely see very similar trend. Like traditionally gas furnace and boiler, we're talking about efficiency from 70%, to 90-something percent. If you use electrical resistance, we're talking about efficiency up to 95 or 99%. But if we use traditional heat pump, it has a COP of 2. And we have more efficient heat pump available today that have a efficiency, COP, of 3 or more. So we are talking about a factor of 4 improvements in terms of water heating systems. So the other technique that's been used as part of the efficiency improvement in buildings is the model predictive control. So our buildings are traditionally operated by rule-based controls, and which is not dynamic, it's not smart, and it's not optimizing the performance. So MPC is all about using the dynamic and real-time signal from the weather forecast, from occupancy forecast, from the loads, and from the pricing signals from the power grid. Then it optimizes the system operation to determine, what should be the thermostat set point, what should be the supply temperature and supply airflow to minimize energy use, carbon emission, or utility costs. So this is the technique that has been developed and applied to office buildings that achieve 44% HVAC energy savings. It was applied to a campus, a central plant that achieved 15% reduction in peak demand. So the growing database developed, compiled by New Building Institute and Navigant, and this database includes net zero energy buildings, including commercial and residential, across different climates in the US. So I'm going to talk about the second dimension of the building decarbonization, and it's about energy flexibility. So as we just mentioned, right, the power grid is changing because there's much more power generation during the middle of the day when the sun is there. And the top figure on the left, it shows California's ISO's power grid electricity carbon footprint. So basically, right, in 2030, we are going to see clean electricity during the middle of the day and during the spring and summer. So then question is, how can we use more energy when the electricity is clean? And how can we reduce energy demand when electricity is dirty or expensive? So basically, as a building owner, you're also caring about how can I reduce my energy use when the utility is expensive, and that's usually between 4 p.m. and 9 p.m. So we're talking about two modes of energy flexibility. One is about load shedding, and that's about techniques to reduce the peak demand. You can dim the lights, turn off some of the products. You can, increase your cooling set points. The other mode is the load shifting. So we're talking about the energy demand, energy services needs during the peak hours get shifted to the off-peak hours. And this can be through technique of energy storage, preheating, pre-cooling, those kind of technologies. Of course, to achieve those energy flexibility, a lot depends on sensing, operation, and optimization of how the energy systems in buildings work. So we still need energy storage technologies to advance that provides high intensity of energy storage at a lower cost and a longer duration. So there's still change in terms of this kind of technology. So the first dimension is the climate resiliency. And resiliency is essential as we are experiencing more extreme weather events that can pose indoor overheating risk to residents. So basically, it implies that the buildings, we must be able to prepare before an extreme event. And during the event, we can lower the heat risk for occupants through some of the passive design and technologies. And when the power is restored, the buildings should be able to restore services, smoothly and quickly. So accelerating decarbonization is an opportunity for us to think about, at the same time, how can we improve resilience of buildings for occupants? So Department of Energy sponsors 3 labs, LBNL, PNL, and NREL, to work together in a project which develop a standardized methodology to assess thermal resilience of buildings. And it starts with how we identified and evaluate the hazard risk, considering the joint probability of power outage and extreme heat or cold events. And then we develop methods through building energy modeling to assess the indoor heat exposure, evaluate baseline and technologies to improve that. And then we estimate the damage to the property when the building's temperature is too low. The water pipe may get frozen, may get burst. People may get sick, right? Because of the temperature too high, and people sometimes even die if nobody take care of them. When the temperature is too high and they cannot move to a safe place. At the end, we put all this together to justify the investment of passive design that valued energy resilience in addition to energy use and carbon emission in buildings. So we have a project funded by California State Global Council called Care Thrive. In this project, we studied 2 disadvantaged communities, Fresno. And this is low-income community. Their air conditioning system is old and inefficient. and is experiencing extreme hot event. Like 2 years ago, it sees 69 days with outdoor temperature higher than 100 degrees Fahrenheit, which is an all-time record. We also survey shows 70% of residents experience different degrees of indoor overheating. So it's a serious problem. How can we help these communities, right, understand and improve the heat resilience? So we engage the community to understand their needs, challenges, and their current practices and culture. And then use modeling as a technique to evaluate technologies and recommend actions to community-based organizations and building residents. At the end, we put all these outcomes together in a heat resilience toolkit to help them. So we model 17 energy technologies, including 9 passive measures. And these are the measures that don't need energy or power to operate. And as you see, a lot is about provide shading to reduce solar heat gain through windows, cool roof, cool wall that reduce the solar heat gain impact on envelope. Solar film also try to reduce the solar heat gain, roof insulation, and nature ventilation. It can be very effective because in hot summer days, when you don't have air conditioning, your indoor temperature can be much warmer than outdoors. So just by opening window can be efficient to help reduce the indoor overheating. We also model 8 active indoor cooling measures. And these includes ceiling fan, active fan, and portable fan that help exhaust heat and help increase air movement that help thermal comfort. We're also looking at modular and efficient air conditioning, like a mini split, air conditioners. So our simulation result shows natural ventilation, as well as cool coatings, window, solar film, and ceiling fans are effective measures to improve heat resilience. The metric we use is the set unmet degree hours. So this shows significant reduction, which is good in terms of improving the heat resilience. However, natural ventilation is effective, but residents express a concern due to security. Opening windows during the night, may not be something they want to do. Sometimes the air quality can be also bad, and opening window definitely, right? It's not a good way to do it. So these are the concerns when we think about actual implementation. So we also model those active measures, and what we found is the ceiling fans can be efficient in terms of reducing the energy use of cooling system. Because when a fan is running, you can have a higher cooling set point, which basically reduces the energy demand on the air conditioning system. So we map all these results together at a city scale, and we focus at a census tract level. So we developed this heat vulnerability index, which considers 3 factors: the heat exposure, including the building's characteristic, population sensitivity, looking at people's age, their sensitivity, pre-existing conditions. Third factor is the capacity to adapt, the income level, do they own air conditioners, are they affordable, right, to run air conditioning during hot summer days, do they close to green park, all these factors put together. And then we color code the census tract level. So basically, the dark gray census tract would be those that the cities, planners, emergency responders want to focus on, when this kind of event is forecast to happen. So we also look at the city level, how waste heat from buildings and transportation influence the urban environment, because we know the urban heat island can be significant and impact, people's life. So we know air conditioning release heat to the urban environment, right? And if we look at the building from the building physics, basically there's other mechanism building release heat, through the building envelope, through the exhaust air from spaces like bathroom, kitchens, but the air handling unit also have some relief air. So it's all these together that right, time waste heat to the urban environment. So we have a project looking at how we evaluate this kind of waste heat from buildings to the buildings in Los Angeles County. So Los Angeles County is a big county. It has 88 cities and about 10 million people. And so we developed this simulation workflow, using WAF to do the microclimate simulation and energy plans to model buildings and calculate the anthropogenic heat from buildings. So our results showed, right, the air conditioning is a significant waste heat source during summer, right? And the whole building, right, sometimes absorb heat, especially during the night when the envelope gets cool, sun is set, and also due to the nighttime sky radiation. We also found the mean daily temperature increase due to heat from buildings is between 1 and 1.5 degree. During the daytime, it's between 0.5 and 1 degree Celsius. During nighttime, it's higher, between 1 degree Celsius and 1.5 degrees Celsius. So nighttime increase can be significant because people will need a cool environment to sleep. If we look at an hourly basis instead of daily mean, it's up to 3 degrees Celsius of increase in urban air temperature, and which can be a significant factor. Think about when outdoors very hot, every degree Celsius increase means a lot to people's life, to energy use because of air conditioning needs. So the last dimension, of course, very important, is the sufficiency-oriented factors. So sufficiency is about reducing absolute energy demand through changes in behavior, use of energy, lifestyle, and collective organization through technology and policy innovations. So an example that differentiates sufficiency from efficiency is, for example, if we want to get to a certain location, right? If we're talking about, taking public transportation, carpooling or driving a small car, and this is sufficiency. From efficiency, it's more like, well, I drive a car that has a higher mileage per gallon, or I drive, electric cars. So that difference is obvious, from that perspective. And so we want to emphasize that reducing consumption is possible while maintaining good living conditions and well-being. So sufficiency is not necessarily meaning sacrifice our comfort or well-being. So IPCC's 2022 report emphasized lower consumption, lifestyle and behavior changes to achieve global climate target. It estimates 17% reduction in global GHG emission in buildings. And for the wealthy nations, that's even higher, up to 25% reduction. And remember, this potential reduction is purely based on the limit or reduction of floor area per capita. If we think about other potentials, for example, we raise our cooling set point. If we condition rooms instead of a whole building as needed, I think that potential savings and reduction in GHG emission will be even much more higher. So some of these are done through demonstrations of affordable housing through these prefabricated techniques. And the project in San Francisco, like the City Space, which won the LEED Platinum certification in 2013, basically this is a compact apartment unit. It enables flexible space layout and furniture to be reconfigured to provide, your needs. So this kind of technology basically also encourage policy to change to basically reduce the minimal apartment unit from square foot of 290 to 220. So these are the examples in terms of sufficiency. So last, I want to just shed some light about building performance simulation opportunities as a community. First is how we model urban systems for building decarbonization. An example, this is the TIER, Time Independent Energy Recovery System. And it shows how can we decarbonize the hot water boiler in large commercial buildings through heat recovery. So basically, traditionally, you have a cooling chillers, and then that times heat through cooling tower, and then you have a hot water boilers. But this new system relying on the conventional chiller, but also heat recovery chiller. There's also air source heat pump, and then there's a thermal energy storage tank. So all these together, basically, the tank takes the condenser water heat, right, storage, and the heat recovery chiller provides the boosting hot water from 100 degrees Fahrenheit to 130 degrees Fahrenheit. And if there's not enough energy in the tank, then the air source heat pump operates to provide that additional heat. And if there's too much heat, then the cooling tower would run to dump the heat into the urban environment. So how can we model these kind of systems? Right, it's a challenge, but it's also an opportunity. We as a community to support building decarbonization. The second opportunity is about the use of AI machine learning technique combined with the building energy modeling to enable us to create digital twins of buildings and communities. So traditionally, AI machine learning have been used in clustering, load forecasting, modeling, controls, natural language processing, smart device, and sensing. So AI machine learning can also be used to support building energy modeling. For example, providing data to improve input, help us analyze output, help us calibrate models, help us create surrogate models that capture input-output relationship, but reduce the computing needs. Of course, they are not going to replace each other. The best opportunity lies they combine to enable us the creation of digital twin that provides user interaction and visualization so that we can see and experience, right, to inform the building design and planning that enables real-time simulation, taking input from building automation system, IoT devices, and power grid to optimize control and operation, to detect another changes to inform operation maintenance. It's also used to track and report, performance. So the last one is we're talking about building decarbonization. We should think about other sector decarbonization, like transportation and power grids. And these sectors are interconnected. So we have to think them together in a holistic way. So basically, we need to consider sectors of energy, water, urban infrastructures, and land use that allow us to consider changes in technology, changes in population, and also changes in climate, so that we can have a holistic solution to decarbonize our economy. So I thank my team, my collaborators, and sponsors. So I stop there. Thank you.
Okay, thanks very much, Tianzhen. That was covered a huge range of topics in that talk, and I think it evidenced the complexity of the challenge facing us. Right, so I'd like to open this up for questions now. We've got about 10 minutes or so, I think, for questions. So I can't see any questions in the chat. And so anyone who could put their hand up if they want to ask a question. I guess the host would be able to see that. I'm not sure if I can. Okay, why? Has anyone put their hand up? I can't. I don't think I can see this. While we're waiting to see, while we're waiting for that, there's one question or one or two questions I have myself, which I can ask for the moment. Okay. Okay, so we've got to, you can see the chat area if anyone pose any questions there. But one question, I was quite interested in this topic of energy sufficiency. It seems to me that it's the next stage ahead, I guess, after energy efficiency, as you explained it. But I suspect it'd be quite difficult to incentivize people to do this. People like bigger houses, they like bigger cars, they like having more material goods. How on earth do you incentivize people to have a more sustainable lifestyle? It's quite difficult, I think.
Yeah, thanks, Paul. Yeah, indeed. I think that's a concept easy to understand. And, there's a huge potential there, but it's also tricky. I think it
Yes.
requires a lot of, social science, training, education. So I'm always thinking like a K-12 schools and maybe have those kind of, concept and training, education might be the way to start with. But I think from a policy point of view, this can be also some incentive, I don't know, through some of the, loan programs or some of the, incentive rebate programs that motivate people, right, to live in a more, this kind of lifestyle. But we've been working with some of the social scientists and behavioral scientists, basically, in this, on this topic. But we are coming from like the more engineers or scientists, right, background. So our interest is also about how can we use technology, right, better design our building and systems to enable people, right, to achieve, those kind of, concept. Like if we can reconfigure a space, furnitures, right? Then not necessarily you need to have a very big, space or buildings or house. So I think this kind of shift takes time, but if we can demonstrate through modern technologies, that would be positive.
Yeah, I know that there's quite often unintended consequences, aren't there? I mean, a lot of the houses where you make it more energy efficiency, then people have uh, increased the heating in the house or increased the cooling. So making it, you don't always get the benefits necessarily that you would like to.
Mm-hmm. Yeah, Paul, definitely. I think that rebound effect is also right, something that right, definitely people also research and.
Okay, so I can't see anyone else put their hand up yet, so I'll keep asking questions until someone does. Another thing that occurred to me is that a lot of these technologies that you're suggesting may be relatively easy to implement in a new building, to make it more energy efficient, to make it more climate resilient, and so on. But I guess the biggest requirement is refurbishment of our existing building stock, because that's obviously much, much larger and a lot more potential there. Have you done a lot of work in that area to refurbishment as opposed to looking at new technologies and new buildings?
Yes, and definitely, I think Paul, we're talking about right decarbonize our buildings. So right, new buildings are only like right 2% of the market. So the majority is still existing building stock. I think the interesting time is right, like every country, the U.S. right has these policy regulation. So we need to right do the energy upgrade to our buildings, right? And we need to electrify our buildings, right? Use heat pump and those kind of things. So the idea then is when we try to do this kind of retrofit, can we also keep in mind, right? We're trying to reduce energy use, carbon emission. We also try to reduce the utility costs. At the same time, can we also ensure these changes will help improve the thermal resilience, the climate resilience of buildings, right, for occupants. So I see this as a right opportunity if we can take this opportunity, ensure, right, we change it once, but we meet multiple goals rather than, currently a lot of the retrofit is done, at a very small scale and also with a very small goal or focus. Of course, sometimes limited to investment or or knowledge support.
Yeah. Okay, thanks. I think we have a question here from Anthony. Do I do that?
Yes.
Yeah. Oh, please go ahead. Yeah.
Oh, no, I just wanted to say, Dr. Hong, thank you very much for the presentation. And also, I meant to just build on the previous conversation about the sufficiency. I'm really pleased to see this being part of, at the Building Simulations Conference and entering into even the discourse to other engineers here. And sorry, it's not a question, it's just a recommendation actually for a book to anyone who's interested on the sufficiency topic. From the area of degrowth, the professor Jason Hickel, who's at the University of Barcelona, from the field of political ecology. So as you mentioned, in the social sciences, and just a really fascinating book talking about some concrete measures that we can take towards sufficiency and examples of sufficiency in other countries, kind of comparing the wealthiest nations to others who have focused on general health indicators and other measures of quality of life. And just really fascinating. And there's, that's the field again, the book Less is More. Authors Professor Jason Hickel, and the field is degrowth. So just throwing that out there. Thank you.
Thanks. I know there are a few interesting projects going on about sufficiency in Europe. So those are also exciting information to check out.
Just the Beyond Growth conference at the European Parliament in Brussels just a couple months ago. And so I guess in the EU, there's discussions about looking more into this and seeing how to build this more into a policy level. So yeah, definitely part of the future as well.
Excellent.
Thanks for that question. I don't think anybody else has raised their hands. I can see. Oh no, there's a question here now. I'll read it out. Now the AI model is becoming powerful. How about the rule-based model or physical model? Do they have any advantages over the data-driven model?
A good question. Yeah. So, as I mentioned in the talk, I think the real opportunity I see is to use them together. I mean, obviously, right, I'm thinking about this AI, black box model. If something, right, we try to model equipment or system, we don't know the physics, right? And then of course you have some data, right? Input, output. Then I think maybe data-driven model is fairly straightforward. But I think when we're talking about building energy modeling, we already have the building physics developed for the last 50 years or a century. And for those kind of application, not necessary, right? You would achieve better performance than the physics-based modeling. But a lot of the time, if you apply both techniques together, I think some of the physics model need lots of input, right? And those are not necessarily easy to get. And some of the machine learning technique may be able to help you, prepare those, better inputs. An example is when you try to model every building in a city. You're talking about big cities. The New York City may have 1 million, buildings. So how can you actually get the input for these 1 million buildings, right? I think there's a lot of sensing imageries and satellites and all those kind of drones and Google Stream Map, whatever, lots of information. And I think through this kind of AI technique, we'll be able to help you figure it out, right? The building's geometry, window wall ratio, the type of constructions, whether the roof has, PVs, has cooling towers, and imagine, right, the opportunities there to apply this kind of AI machine learning technique to basically extract those information as a nice input to our building energy model. At the same time, those two techniques work together. They can also create very powerful synthetic data set. So sometimes we have data from measurement. We may have data from our simulation, but quite often these two techniques combined together, they can create very powerful synthetic data set and then actually benefit both. for your machine models, training, validation, but also used to, compare results from a simulation, or even used to calibrate your models.
Okay, thanks very much. Okay, I think we've actually reached the the time for the end of the talk, 10:45. So I think we ought to keep to schedule. So I'd like to thank our keynote speaker, and a very wide-ranging, interesting talk. And I think you've pointed out that we're going to keep busy as researchers for a long time to come. So thanks very much again, and thanks for those who joined into the talk. I guess it'll be available also, has been recorded for those who haven't been able to make it. So thanks everybody, and enjoy the rest of the conference.
Thank you, Paul, and thanks everyone. Enjoy the conference.